So good morning or good evening, depending on your local time. My name is Tito Andriolo, and I'm a researcher at the Technical University of Denmark. And the presentation, the work I'm going to show you today is the outcome of a collaboration I had with Barbara Kuznetsova from Eindhoven University of Technology in the Netherlands. And the topic is the size of the cyclic plastic zone in metals containing elastic particles. So, as we all know, the size of the plastic zone is a key quantity when it comes to fatigue crack propagation. From one side, it gives us some information about the nature of the crack propagation process. And on top of that, it also allows us to understand whether or not the component or the structure containing the crack can be considered elastic at the macroscopic level. So during one loading cycle, it is common to distinguish the forward and the reverse plastic zones, which form as the stress intensity factor attains its maximum and minimum level respectively. So under plane strain, there is a well-known formula that allows you estimating the size of the forward plastic zone, which is usually the quantity of interest. And as you can see here, this formula states that the size of the plastic zone is proportional to the ratio between the maximum stress intensity factor and the material yield stress squared. And the proportionality coefficient can be taken equal to 0.1, which is an average of the published literature. But the very key point of the formula that we want to make here is that this formula was actually derived under the assumption of material homogeneity. So what happens if the material is not homogeneous, but contains heterogeneities whose size is comparable to the size of the plastic zone? And I want to remark that this is actually not a very uncommon scenario, especially if you work with metals containing micron-sized particles like standard metal matrix composites or spheroidal graphite irons. And here I have an example of a common grade of spheroidal graphite iron whose microstructure contains these graphite particles here. So if I use the formula to compute the size of the plastic zone near the fatigue threshold, so when we expect a crack to start propagating, then I find a value of 150 microns. And this is comparable to the distance between the particles, as you can see from the marker in this micrograph. So in a situation like this one, is this formula reliable or not? So this is the question that we wanted to answer in this investigation. And to do that, we investigated using a model the size of the cyclic plastic zone in an idealized two-phase composite. And we showed this composite to be as simple as possible, made of an elastic, perfectly plastic matrix containing elastic spherical particles. And on top of that, we also assumed the interface between the particles and the matrix to have infinite strength. So the particle size and spatial distributions were generated based on the graphite particles contained in a small volume of spheroidal graphite iron. And here you see the distribution of the particle diameters as well as the distribution of the particle distance to the nearest neighbor. So for an idealized two-phase composite like this one, we only need 5 parameters to describe the elastic and plastic parameters of the particles and of the matrix, which are the Young's modulus or Poisson ratio of the particles, Young's modulus, Poisson ratio of the matrix, and the yield stress of the matrix. And we selected 2 sets of these 5 parameters in order to represent the behavior of spheroidal graphite iron and of aluminum containing silicon carbides. And for each of these 2 sets of parameters, we estimated the effective behavior of this idealized composite by subjecting this representative volume element to uniaxial testing. And by doing that, we found the effective Young's modulus, effective Poisson ratio, effective yield stress of the composite, as well as this parameter here, WPO2, which is the plastic work for loading, for monotonic loading up to the yield point. And as I mentioned before, our aim was to develop a model to investigate plasticity in these idealized two-phase composite. And this is a multi-scale model that we have used that consists of a model at the macro scale, which represents a compact tissue specimen made of this composite material. This microscale model consists of a crack, contains a crack which is stationary and is 4.5 millimeter in length. And we load this model by applying a time-dependent force to the loading pin in order to recreate a situation of constant amplitude loading with a positive fatigue ratio. And at any time, for any value of the force applied to the loading pin, we determine the stress intensity factor at the crack tip by applying just standard formulas. So on top of this 2D macroscale model, we also have a 3D microscale resolved model that corresponds to the region surrounding the crack tip. And this microscale resolved model consists of an outer region made of homogenized material. So we use the effective properties of the material to describe the behavior in this outer region. And then there is an inner region which is adjacent to the tip of the crack, in which the microstructure is fully resolved. So we distinguish the particles from the matrix. And we use the displacement field computed with the macroscale model to apply the boundary conditions along these four faces here of the microscale model. And regarding the faces perpendicular to the y-axis, we use just standard periodic boundary conditions in order to account for the presence of the surrounding material through the thickness of the specimen. So now let's come to the results that we have obtained. So in order to identify the amount of plasticity forming in the matrix, we computed the plastic work during a loading cycle, and we normalized this quantity by the plastic work for monotonic loading of the composite up to the macroscopic yield point. And here is a contour of this normalized cyclic plastic work over a cross-section perpendicular to the thickness of the model. And please note that here the coordinate axes are normalized by A, which is the mean particle distance. So as you can see here, in front of the crack, at the tip of the crack, which is the crack is just this black line here, plasticity seems to be very much affected by the local particle distribution. But in particular, it looks like plasticity tends to connect together neighboring particles, forming some sort of chains. And this is something that we also see even to a smaller extent when we use the properties of aluminum reinforced with silicon carbide instead of the properties of spheroidal graphite iron. So I would say that in both cases, it is quite clear that the particle spatial arrangement has a strong impact on how plasticity propagates at the crack tip. And this was just the result of plasticity spreading over one cross-section. So in order to have an information, sort of a 2D representation that conveys information over the entire 3D volume of the model, what we did was to calculate the mean value of the normalized plastic work through the thickness of the model. And this is the corresponding contour that we consider representative of the plastic zone shape in this composite material. So as can be seen here, the boundary of the plastic zone is very irregular, and this is due to the presence of the particles. But as a whole, the plastic zone is symmetric with respect to the crack, and this is in agreement with the symmetry of the loading and the symmetry of the specimen geometry. And I want to emphasize that an advantage of this 2D representation is that we can easily make a comparison with the size of the plastic zone predicted by replacing the microstructure in this microscale model with the homogenized material. And this homogenized material is something that we have modeled using von Mises plasticity with a kinematic hardening. So what can be seen here is that this magenta line that represents the boundary of the plastic zone predicted according to the homogenized model is actually much smaller compared to the size of the plastic zone that we predict using the fully resolved microstructure model. So in order to investigate further these results, that it was quite interesting in our opinion, what we did was to compute the size of the plastic zone for several values of the maximum stress intensity factor. And we measure the size of the plastic zone in terms of the plastic zone, the square root of the plastic zone area. And this is something which is quite robust to the fact that we have a very irregular boundary of the plastic zone. And this is the outcome. So you can see that the homogenized model, the prediction of the homogenized model, which is represented by this blue line here, is always smaller than the prediction of the model with a fully resolved microstructure, which is this green line here. Doesn't matter the value of the maximum stress intensity factor. So there can be two reasons for this. One is that for Mises-based plasticity is maybe not the best way to model plasticity in an idealized composite like this one. And then the second reason is that an idealized composite like this one actually shows a continuous transition from the elastic to the plastic behavior. And this is something which is quite difficult to capture with the standard plasticity models. And then finally, I also want to emphasize that here we have a third curve, the one in red, which actually represents the prediction of the analytical formula that I showed you at the beginning of the presentation. And I would expect this line to overlap the blue line, so the prediction of the homogenized model, as both are based on the assumption of a homogeneous material and von Mises-based plasticity. But you can see that there is a discrepancy, and I believe that this discrepancy is due to the fact that when we compute the square root of the plastic zone area from the analytical formula, then we have to make an assumption for the shape of the plastic zone. And this is probably what causes this discrepancy. But in any case, what I really want to emphasize, so the takeaway message of this slide here is that both the homogenized model and the analytical formula underestimate the size of the plastic zone. And this was a very important result. So in order to see if this was just a coincidence due to a particular choice of the model parameters or not, we performed a very thorough sensitivity analysis. So in this model, there are 10 parameters that affect the plastic zone size, 2 parameters related to the loading, then 5 parameters related to the elastic and plastic properties. And then for the microstructure, we have the mean particle distance, the particle volume fraction, and then this psi is a set of dimensionless quantities that describe the particle size and spatial distribution. So if we just neglect this psi parameter for first approximation, then we can write that the size of the plastic zone has to be a function of all these remaining 9 parameters. And here for convenience, we just replace the yield stress of the matrix with the yield stress of the composite. This is something that is more easily accessible in experimental investigations. And then we can apply the Buckingham pi theorem in dimensional analysis to rewrite this expression in terms of a relationship between dimensionless groups of quantities. And this is what we have done here. And I want to emphasize that we have chosen these dimensionless quantities in a special way so that these first 2 dimensionless groups that you see here correspond to the quantities that we had on the y and x-axis on the previous slide. So that means that if we want to study the sensitivity of the model results, we can just look at how the relationship that I showed you in the previous slide is affected by the values of these other dimensionless parameters. So let's have a look at what happens if I start by changing the load ratio here, R. So as you can see, it's not something that affects a lot the relationship between the size of the plastic zone and the maximum stress intensity factor when these 2 quantities are normalized in this way here. And then if I try to change the yield stress of the composite, then again I see negligible differences. And I find exactly the same if I try to change the elastic properties. Here I've switched between the elastic properties of modular cast iron and the elastic properties of aluminum with silicon carbide. So you can see that there is an effect on this relationship here, but the effect is definitely minor. But what is most interesting, I would say, is that when I start playing around with the particle volume fraction, then I see that the larger the particle volume fraction, the steeper these curves become. And this is something quite interesting, which actually means that if I take two materials with the same yield stress and I load them in exactly the same way, then the material with the higher volume fraction has also a larger plastic zone size. And this is something that the standard formula that we use to estimate the size of the plastic zone cannot account for, because according to that expression, if two materials have the same yield stress and are loaded in exactly the same way, then the size of the plastic zone has to be the same. So in order to compensate for that, we have come up with a new formula to estimate the size of the plastic zone. And we started from this general expression that we have obtained using the Buckingham-Hyde theorem. So because there is always a linear relationship, or approximately a linear relationship between these and these second dimensionless quantities here, then we can rewrite this expression in this simplified form, in which this psi function is simply the slope of the previous curves, of the curves that I showed you before. And as we saw, this slope is not much affected by these parameters, except for the particle volume fraction. So that eventually we are left with this simple expression that states that the size of the plastic zone measured by the square root of the plastic area is given by a function of the plastic zone size times the ratio between maximum stress intensity factor and material yield stress squared. And the only thing we don't know here is the shape of this psi function, but this is something that we can obtain by fitting a large number of numerical situations. And what you see here is actually the outcome of this data fitting procedure. So to summarize, in this work, we have used a multi-scale model to investigate crack tip plasticity in idealized composite during cyclic loading. And what we have seen is that the presence of the particles modified the shape and the size of the cyclic plastic zone compared to what we would expect based on the hypothesis of homogeneous material behavior and plasticity driven by the von Mises stress. And particularly, what we have seen is that for the same material yield stress and loading conditions, then the material with a larger particle volume fraction also has a larger plastic zone. This is something that the standard formula cannot account for, and because of that, it can underestimate the size of the plastic zone by as much as a factor of 3 when the particle volume fraction is 20%, which can really be a lot, actually. So to compensate for this, we propose a new formula that is here, and I didn't have the time to show that to you, but it turns out that this formula is also robust to minor particle deviations from the spherical shape. So the main advantage of this formula, as I mentioned before, is that it can account for the effect of the particle volume fraction on the size of the plastic zone. So if you want to read more about this work, you're more than welcome to take a look at this article that was recently published, or to contact me at this email address. So this is the end of my presentation. I really thank you for your kind attention, and I will be super happy to answer any questions you may have.